So in this experiment, you'll be exposed to know how to calculate amount in gram and how to prepare a standard solution. So the title of this experiment is Primary Standards and Preparation of Standard Solution. You'll be exposed to know how to prepare a standard solution. I'm going to illustrate that also, and how to calculate the amount in grams before you prepare the standard solution of a known concentration. So overview, we can look at standardization. Let's start from there. What is standardization? What is the process all about? So let's start with the basics. Standardization is just the process of finding the exact concentration, is a process used in finding the exact concentration, okay, of a prepared solution, okay, using a standard solution. So you use a standard solution to find the concentration of the unknown solution, okay. Now, a standard solution is a solution of known concentration. A standard solution is a solution of known concentration. All right. So, and it is used in standardization. We employ it to determine the concentration of the prepared solution. All right. The standard solution is a solution of known concentration, while standardization is the process of finding the exact concentration of a prepared solution. All right. So now we have types of standard solutions. So we have some types. We have types of standard solutions. We have types of standard solution. You're expected to know. We have a primary standard solution, and then we have a secondary standard solution. So these are the types of standard solutions. Bear in mind their concentrations are known, okay? One could be known, one could be unknown in an acid-base reaction. So it varies. So basically we have two types of standard solution, all right? So for the primary standard solution is just a solution of a substance with a known exact concentration with the following requirements. So it has some characteristics. So now we have one, and that if you look into your manual, you will see some of them, okay? But the basic requirements for a primary standard solution, don't forget, the primary standard solution is used actually to standardize secondary standard solutions. So a primary standard, any substance acting as a primary standard, all right? Any substance acting as a primary standard is actually used to standardize a secondary standard, all right? So we have a secondary standard solution, all right? The primary standard solutions are used to standardize the secondary standard solutions. In any case, their concentrations are known. So the basic requirements for a primary or for primary standard solutions are: it must be of high purity. I don't think I'll keep writing that, high purity. So it must be of high purity, usually at around 99.5 to 100 degrees Celsius, right? 99.5 to, it must be very, very pure, of high purity, and made from standard substances with definite chemical composition. Now the second one, it must be stable, meaning that if it's stable, that means it is less reactive. So it must be stable, highly stable, which implies it should be less reactive, and it has to be inexpensive and plentiful. So it must be cheaply available and plentiful, inexpensive, okay? And we could say that it should not be associated with any water molecule, all right? That's number 4, right? It should not be associated with any water molecule, meaning that it should not contain water of hydration. Water of hydration must be absent. So that is what it means. It should not contain any water associated with it. All right. So now it should also have what we call high equivalent weight. I'm going to explain this now. I'm going to illustrate this. So it should have a high equivalent weight so as to reduce relative error. All right. So as to reduce relative error associated with weighing. So it should have a high equivalent weight to reduce relative error associated with weighing. I'm going to give an example of that. I'm going to illustrate this high equivalent weight just for you to know. It's not something that is part of your manual, but you're supposed to know what an equivalent weight is. How is it gotten? What is it all about? How does high equivalent weight reduce relative error associated with weighing? It could be a question, but your knowledge of this could help you, all right, understand the concept better. So let's illustrate high equivalent weight. So to illustrate this, a primary standard should have high equivalent weight. So what it means that if a primary standard have high molecular mass, a primary standard having high molecular mass, it is sure to give us a high equivalent weight. So a primary standard with high molecular mass, all right, will give us a high equivalent weight. All right, and this high equivalent weight will help us to weigh accurately on a balance with reduced error than a primary standard with a low molecular mass, which implies low equivalent weight. All right, so less error will be incurred here, but much error will be incurred when the primary standard has low molecular mass, which implies low equivalent weight. Now, what is equivalent weight? Let us talk about that a bit. Equivalent weight, I'm abbreviating this, okay? So equivalent weight is just the weight of substance that reacts with 1 mole of another substance or 1 mole of hydrogen ion present in the other substance, okay? So now the weight of substance that reacts with 1 mole of another substance in a chemical reaction is called the equivalent weight. The weight of substance that reacts with, let me use this, weight of substance that reacts with 1 mole of another substance carbonate, let's take for example, sodium carbonate, right? You know, it has a molecular weight of, when you calculate the molecular weight of this, all right, you're going to have 2 times 23 plus 6 plus 12 plus 3 times 16. So it's going to give you a total of 106 gram per mole. So we have sodium carbonate, for example, that has molecular weight of 106 gram per mole. So it means that in acid-base titration, let me use ABT, all right, it should react with 2 moles of hydrogen ion. It reacts with 2 moles of hydrogen ions, right? So if, for example, we have the sodium carbonate plus tetraoxosulfate 6, you know tetraoxosulfate 6 has hydrogen ions, right? two of them, right? So this is tetraoxosulfate 6. So tetraoxosulfate 6 has two ions, right? So that means sodium carbonate with this molecular weight in acid-base titration reacts with 2 moles of hydrogen ions, which is basically acid-base titration. Okay. Now we can say, therefore, its equivalent weight. How is it calculated? How do we calculate it? For a substance that has a molecular weight, because equivalent weight is related to the molecular weight. Okay, so its equivalent weight now will be, let me wipe this off. Its equivalent weight will be molecular weight divided by the 2 ions, right? So what this means is that we're going to divide 106 by 2, which is what? 53 grams. So this is the equivalent weight, all right? 53 grams per mole. This is the equivalent weight of sodium carbonate in an acid-base titration. As you can see, it's actually high. It's actually high enough. Can you see that? So this means that this can actually serve as our primary standard, because primary standards are supposed to have high equivalent weight. Okay? In a nutshell, if we say we want to weigh 0.1 gram of a primary standard, all right, to standardize a given solution. Now, a small error of 0.01 gram could be incurred. This 0.01 gram depends on the balance that is being used. You already know this is specific to a top loader. So, if you're weighing this amount of a primary standard, the equivalent weight of a primary standard being 0.1, let's say for example, an error of this could be encountered. Now, a small error being encountered by this means that if we want to calculate the relative error, is equal to error over actual value times 100%. Now it means that the error is what? 0.01 divided by 0.1. 0.01 divided by 0.1 times 100. Now if you calculate this, you'll be having 10%. Can you see? This is a very small amount, okay, of an equivalent weight that is being taken to be weighed, and you're having this sort of error. It means that your relative error will be so significant. You see, 10% is so much. It's a big error because you have a low molecular or low equivalent weight, right, of your primary standard. So this is a low molecular mass and low equivalent weight. So the error encountered during weighing due to the balance, a balance with such error could result in a very high relative error. Alright? So in that case, what this implies is that the prepared standard solution or the prepared secondary standard solution could be 10% off. What I mean by off is this: from the desired concentration using the primary standard. So you're going to have a total error that is 10% off from the actual concentration you want to determine. So this is the essence, because we have a very small low equivalent weight. Now let's take for example, okay, in a case we have, let's say we took 10 gram of the primary standard and we encountered the same error of 0.01 gram. What will be the relative error? The relative error, which is what? Error over actual value. What is the error? 0.01 divided by 10 multiplied by 100. So if you do this correctly, you should have 0.1%. You see what this means? Is that the prepared standard solution could be only 0.1% off from the desired concentration. You see, using the primary standard. So this error is very reduced and minimal. So for a primary standard to be suitable, it should have a high equivalent weight. Alright? Which means that the error is reduced. But in a case where the equivalent weight is very small, like in the previous example we had, you see that the error is off or was off by 10%. So this is just an illustration for you to understand what relative error equivalent weight is all about. Now, before we go into preparation of standard solution and how to calculate the amount in grams, I need you guys to know the difference between a primary standard and a secondary standard. There are differences, alright? It's important because in the course of your experiments that you are yet to conduct, you'll be seeing these terms, alright? Now, primary standard, just as we said earlier, they are highly pure. The primary standards are highly pure. And they serve as reference materials or reference points in experiment. That they serve as references, all right? And what this means is that you use them to standardize, okay? That of the secondary standard, okay? Now, why the secondary standards are standardized? The secondary standard is primary standards. The secondary standards are standardized using primary standard. You see, they serve as reference. The primary standards are reference to the secondary standards. So the secondary standards are standardized by making reference to the primary standards for everyday analysis or an experiment. And the secondary standards are not as pure, okay? They are less pure. Alright? You see? The secondary standards are less pure compared to the primary standard. And that is why we sometimes do calculate percentage impurity, percentage purity. It is talking about the secondary standard. So it has to do with some of these titrations you get acid-base titration, you have to calculate percentage purity. That is the secondary standard. Okay, so that is basically it. Primary standards are very pure, secondary standards are less pure. Alright? So in an acid-base titration, for example, because this is what this experiment, this course is all about, and some other sort of titration, redox titration and the rest. So you know this is your burette, and this is your Elimea flask, or you call it your conical flask. This is the burette. So in the burette, you put the standard solution. So we've come back to standard solution. The solution of known concentration goes into the burette, right? Why the solution that you want to determine the concentration, we call it the analyte. Analyte is what we call it. Now the solution in the burette has a name, we call it the titrant. Why that in the conical flask that is pipetted is called the titrant. Alright, you should know these differences. Now essentially, the primary standards are used to standardize the secondary standard. Alright, so this is basically it. Now let me give you guys some few examples of primary and secondary standards. So let's say secondary standards, let's say primary standard. So these are secondary standards, these are primary standards. We have such examples such as sodium carbonate that we mentioned before. We have such example as oxalic acid, alright? Then secondary standard, we have such examples such as sodium hydroxide. Then we have such examples such as potassium permanganate. Now, if you look closely, alright, let me write this clearly. This is employed in acid-base titrations, while these ones are employed in redox titrations, which you will be carrying out either in the fourth practical, okay? You'll be carrying out redox titration, alright? So these are examples of primary standards, okay, and secondary standards. These are used in acid-base titration, and these are used in redox titrations, which is oxidation reduction reaction. So that will be done later on, okay? Now, we'll be going into calculating the amount in grams and how to prepare a standard solution. How is it prepared? I'm going to show you guys how it's prepared. So how do you calculating amount in grams? Amount in grams. All right. How do you calculate amount in grams, and how do you prepare a standard solution? This is what we're going to do, and I'm going to show you guys two methods to calculate amount in grams, right? And subsequently how to prepare a standard solution, right? So we are going to look at an example. Let's say you are asked to calculate the amount in grams required to prepare, let's say, 0.5 liters of 0.25 molar sodium hydroxide. All right. So the question says calculate the amount in grams required to prepare 0.5 liters, all right, of 0.25 molar. This is the concentration, this is the volume, and this is the substance you want to prepare. You want to calculate the amount in grams required to prepare this concentration in this volume. Okay, so what it means, we're going to look at two methods. Now, before you do any calculation, try to interpret what the question is all about. Now, the first method we'll be looking at is method 1. All right. Method 1 has to do with using the chemical formula or the equation, chemical equation. So there is a formula which we use. Molar concentration is equal to mass concentration divided by molar mass. Can you see that? Now, there's basically what you're supposed to know is about the units. When you look at this unit, let me interpret the units for you. Now, molar concentration has its unit as capital letter M or mole per dm cube. That is what molar concentration means. Okay? While mass concentration has its unit as gram per dm cube. Okay? While molar mass, it's important to note this unit. It can save your life. Molar mass has its unit as gram per mole. Yeah, there was a class that was supposed to know this. I told them to know this very well, but this is it. Okay, molar concentration is in molar or mole per dm cube. Molar means mole per dm cube. 1 mole is 1 dm cube. So mass concentration is gram per dm cube. Molar mass is gram per mole. So with this basic understanding, this is our molar concentration, which is 0.25 mole per dm cube or 0.25 molar. Now this is volume, liters. Liters is volume. Okay, this is capital letter L. Now another insight I need to give you is that 1 liter is equivalent to 1 dm cube, and 1 dm cube is equivalent to 1000 cm cube. All right. So it means that this 0.5 liter is half of 1. So 1 liter is, so 1 dm cube would be 0.5 dm cube if you want to convert, and 0.5, which is half, that means this is 500 cm cube. This is just for you to interpret this. 0.5 liter means 500 cm cube or 0.5 dm cube, because 1 liter is equivalent to 1 dm cube. So with this knowledge, let's apply this formula. and solve the amount in grams, which is gram per dm cube. The amount in gram is your mass concentration. So that is it. Now let's do this here. So the amount in gram is the mass concentration. Your molar mass is the sum total of the individual atoms for this particular compound. Molar mass, you already know how to do that. Sodium is 23, oxygen is 16, hydrogen is 1. Usually the values are given. So once you sum them all up, you have 40. That means the molar mass of sodium hydroxide is 40 gram per mole. Molar concentration is 0.25, so this is 0.25. Sorry, my marker is failing me. Let me switch over. So this is 0.25 is equal to mass concentration is what we are looking at. So let's call it an X. Molar mass is what? 40 gram per mole. Y here is mole per dm3, right? Or molar, okay? So once you've done this, you can cross multiply. X times 1 is X. 0.25 times 40 is 10. So we're going to have 10 gram per what? Per what is it going to be? Per dm cube. Alright? Because we are calculating in the order of molar, mole per dm cube. So, having arrived at this, you come back to this question. It says how much is going to be in 0.5 liters. So how much will be in 0.5 liters? So I'm going to wipe this off just to continue. Since we have 10 gram in 1 dm cube, which is 1 liter, okay, which is also 1000 cm cube. So how much will be in 0.5 liters, which is what? 500 cm cube. Look at this, look at the liters, look at the units. So now what this means is that X times 1, X, 10 times 0.5, what is it going to be? It's going to give you 5. So this is going to be 5 gram per 0.5 liters. This is the answer. So this is how you calculate using the first method. Alright? This is how you calculate it. And what this means is 5 gram in 0.5 liters. It can also mean 5 gram in 500 cm cube. So the second method is just using the ratio. So let's have the second method. Remember what our question is, 0.5 liters of 0.25 molar sodium hydroxide, right? So the second method, what we are going to do is we're going to use a form of ratio. So let's have method 1. Method 2, sorry. Method 2, you have to start from the basics, okay? Since we are talking about sodium hydroxide, so 1 molar concentration of any substance is the molar mass of that substance in 1 dm cube. This is the relationship. So 1 molar concentration is the mass of 1 molar substance dissolved in 1 dm cube. Now, in the question says 0.25 molar. So I'm going to have 0.25 molar. How much is in 1 dm cube? So from here we cross multiply. 40 times 0.25 will be equal to X times 1. And if you do this, you get 10, which is 10 gram per dm cube. Alright? So with this, you still do the same thing we did earlier. If 10 gram of sodium hydroxide is dissolved in 1 dm cube, alright, which is 1 liter for this particular question, then how much will be in 0.5 liters? Cross multiply. X 10 times this is 5 gram per 0.5 liters. So that is the answer. This is the second method. So it's quite clear. And then, how would you prepare such concentration? How would you prepare 5 grams of 0.5 liters sodium hydroxide? Now, that will take us to preparing a standard solution because we know the concentration. So how would you prepare 0.5 gram of 0.5 gram is how much liters? Sorry, how would you prepare 5 gram of 0.5 liters sodium hydroxide? Alright, how would you prepare what we've just calculated? So it means that you're going to dissolve 5 gram in 0.5 liters. So you're going to dissolve 5 gram in 0.5 liters is half of what 0.5 liters? 1 liter is, let's show this, 1 liter is 1000 cm cube. Alright, so 0.5 liters will be equal to x. X times 1, x, 0.5 times 1000, so that will be 500 cm cube. So how would you prepare 5 gram in 500 cm cube sodium hydroxide? So it means that you need a standard flask. A standard flask is a volumetric flask. It looks like this. So you take the size of 500 cm cube. You need a 500 cm cube standard flask. All you have to do is weigh 5 gram, introduce it into the flask. 5 gram sodium hydroxide goes in. Alright, then add some distilled water to dissolve it completely. So you add distilled water. Distilled water goes into the standard flask to dissolve it completely. The standard flask has a graduation, a mark, okay? Once it has sufficiently dissolved the 5 gram, you've sufficiently dissolved the 5 gram in distilled water, not so much that it fills up, dissolve it sufficiently, then you keep adding distilled water till it reaches this mark. So once it has reached this mark, that means you've prepared exactly 5 gram in 500 cm cube, which is 5 gram in 0.5 liters of the sodium hydroxide. So I will be demonstrating this in the class so that you will understand the practical aspect. So this is basically what this experiment, primary standards and preparation of standard solutions is all about.